Today we will discuss about chapter 9, which is transportation, assignment and network models. In this chapter, we will use linear programming problems for transportation, transshipment and assignment models, and we will see how to solve these problems using different methodologies like shortest route, maximal flow problems and minimum spanning tree problems and so on. So let's start this chapter. Linear programming is a area where we have studied about in the past two chapters. This could be used, programming problems can be modeled as network flow problems. They are like transportation problem, transshipment problem, assignment problem, maximum flow problem, shortest route problems, minimum spanning tree problem, and there are many other specialized algorithms as well. So in the case of network models, every point on the network is referred as a node, which is represented as a circle or a rectangle or a square. And those that connect these nodes or lines are called as arcs. So let's talk about the first type of problem, which is called transportation problem. As the name indicates, here we want to deliver some items from some source to destination, like sending an email from a source to a destination. And given the capacity of the goods, given the capacity of the items you want to send from the source to the destination, you need to meet some requirements. We also want to minimize the total transportation and the production cost. So let's see how to solve such a problem. Here is an example where we have a transportation problem where we want to minimize the cost, we want to meet the demand, and we should not exceed the supply. So let's say we want to send an item from source I to destination J. It is represented by Xij, and the source locations and the destination locations are given here. So we want to deliver from Des Moines to Albuquerque or Boston or Cleveland or whatsoever. So here to represent them, X11 says we want to go from the first source to the first destination. X12 from the first source to the second destination. For each one, the cost is given. So you just multiply them with the respective cost and you sum it up to get the total cost. You need to minimize it using a linear program. And then the constraints are the source can supply only 100 items. So the first source can supply maximum of 100 items. So X11 means source 1 to destination 1, which is the same. X12 from the source 1 to destination 2. So source 1 to destination 1. Source is Des Moines and the destination is Albuquerque. And source 1 to destination 2. Source is the Des Moines to Boston, and source 1 to destination 3, which is Des Moines to Cleveland. So the sum of this will be less than or equal to 100. If you talk about the demand, you should meet the demand. You cannot be less than or greater than the demand. So for a destination, you have a demand of 200, let's say for Boston. So this is X12 plus X22 plus X32, meaning from any source, 1 or 2 or 3, you have to reach the destination, which is Boston, which is 2, number 2 here. And Xij greater than or equal to 0, this is indicating the non-negativity. These things can be solved using any software and you can get solutions. So here is the representation of it, network representation of the transportation problem. This is the source, which is source 1, 2 and 3, destination 1, 2 and 3. For each combination, there is given what is the cost from source 1 to destination 1 is $5, source 1 to destination 2 is $4 and so on. The supply from each source is given and the demand is also given here. It is represented here using the network representation. You can solve these things using some software like. So in a general way of representing transportation problems using linear programming model is Xij, where shipment from source I to destination J. Cij is the cost of one unit from the source I to destination J. Si is a supply at source I. Dj is a demand at destination J. So you might have, for example, in a transportation problem, m number of sources, n number of destination. They can be different numbers, they can be same. So the number of variables will be m into n and the number of constraints will be m plus n. So minimize the cost, Cij, which is the cost of each entity, one unit transfer from source I to destination j into Xij, which is representing it, sum of it. So summation j equal to 1 to n, summation I equal to 1 to m. So it should be I equal, not I minus 1. So you sum it up to get the minimized cost, and then you have the constraints. Source should be greater than or equal to, so Xij summation j equal to 1 to n, which is representing less than or equal to Si, and Xij is equal to Gj, which is meeting the demand. So here, if you watch out, you can see it is summation j equal to 1 to n for the source, because xi will be the same. Xi, the I in x and the I in s will be the same, and the j will vary from 1 to n. Similar in the case of dj, which is the demand of j, the I will vary, the source will vary, but the demand will not vary. And xij greater than or equal to 0, this is the non-negativity constraint. The second type of problem is called assignment problem. Okay, here we want to assign some people some particular tasks or some equipment, some job like. Here again, we want to minimize the total cost or the total task time. And you can see the assignment problem is a special type of transportation problem. Why? You will find one guy will be allocated to one job. So simply saying, each person may be assigned to one job or one project, and each job should have one person. So you cannot say a job which is not assigned to anybody, or a person is assigned to two jobs. This is not allowed in the case of assignment problems. Here is an example. There is a shop called Fix It Shop. They want to repair three items: a radio, a toaster oven, and a coffee table. And they have three kinds of people who can do different jobs like, and they want to allocate them to each one. So idea is to minimize the total cost, because you have to pay for the workers. So three people names are given, the persons are given. Adam is source 1, Brown is 2, and Cooper is source 3. And the project is project 1, 2, and 3. For each one, the cost is given. If you ask source 1 to do the project 1, he will charge you $11. And if the source 1 is going to do the project 2, he will charge you $14, and others are also given. Supply demand will be 1 each, because remember, it's an assignment problem. 1-to-1 mapping should be done. So how to represent it? Xij. So I is the person, j is the project. Xij can be 1 if the person I is assigned to project j. It will be 0 if he is not assigned to. If person 1 is not assigned to project 1, then it will be x11 will be 0. If he is assigned, then it will be 1. And 1 I is given, and j is also given, 1, 2, 3 for the persons, and 1, 2, 3 for the project. So how to calculate and minimize the cost? You already, for the person 1 to do the job 1 will be $11. So 11 into x11 plus 14 into x12, and so on for each one of them. Sum them up. So you need to minimize this total cost. Then x11 plus x12 plus x13 equal to 1. Why it is equal to 1? So if you see, either person 1 is assigned to job 1, or the person 1 is assigned to job 2, or the person 1 is assigned to the job 3. So he can be assigned to any one of them. Okay. So some of them should be 1. He cannot be assigned to more than 1. So the value will be either 0 or 1. It can't be anything else. On all the right hand side, the constraints will be equal to 1, not less than or equal to, or not greater than or equal to. And you could note here, xij can be either 0 or 1, depend upon whether he is assigned or not assigned. And you can solve it using some tools to get an answer. The third type of problem is called as transshipment problem. Here I have a source, you have a destination, plus you have an intermediary point. So it doesn't go directly from the source to destination. There is somebody in the middle, or some location in the middle, through which the data has to be transferred, or the item has to be transferred. This is called as transshipment point, or the transshipment problem. So here they are taken an example. They are making some machines, which is manufactured at some places like Toronto or Detroit. It has to be transferred to regional distribution centers, which are available at 2 places. And finally, they have to be transferred to some supply houses, which is available at somebody else, some other place. So you cannot go from the from the source to the supply house directly. Okay, it has to go through the middle one. So here is a representation. Source is there, which is Toronto and Detroit. This is the source, and the destination is New York City, Philadelphia, and St. Louis. It has to go through Chicago and Buffalo, and the connections are given. Supply from each source is given, demand from each one is given as well. So this is called transshipment. Why it's called transshipment? Because there is an intermediary, which is called as transshipment point. And the rates are given. If I want to transfer from Toronto to Chicago, it is $4, and so on and so forth. All the rates are given here. Demand for each of the destination is given. Supply for each of the source is also given. So we need to minimize the cost out of it. How to minimize? Based on some constraints here. Remember, Toronto can maximum supply 800. Detroit can maximum supply 700, not more than. And the number of equipments which has to be sent to New York City should be 450, because it is demand. You should not go beyond. Also, you cannot deliver less number. Okay. Similarly for Philadelphia and so on. And you have to understand for the intermediary nodes, which is the transshipment point, Sigako and Buffalo, how many units come in is how many goes out. So incoming is equal to outgoing for each of these transshipment point. So these are constraints. So decision variable is xij from location I to destination j. So if you take, for example, 1, 2, 3, 4, you can have 3, 4, 5, 6, 7. Why 1, 2, 3, 4? Source is 1 and 2. And then from 1 and 2, it can go to 3 and 4. So it will become 3 and 4 in the destination. From 3 and 4, you can deliver to 5, 6, 7. Okay. So it cannot be delivered to itself, but it can go to 5, 6, 7. From 1 and 2, you cannot deliver to 5, 6, 7. It will go to 2, 3 and 4. Remember, the node numbers are given here. Node 1, node 2, node 3, node 4, and 5, 6, 7. So let's talk about the minimization of the cost is 4 into x13. So if you want to deliver from 1 to 3, it is $4, and then for each one you represent it. x13 plus x14. So supply from 1 to either to transshipment point number 3 or transshipment point number 4 is less than or equal to 800. Why only x13 and x14? Because you cannot supply to anybody else. From Toronto, it can be either to both of the nodes, either to the transshipment node number 3 or transshipment node number 4, nothing else. Similar from Detroit as well. And then you can see 3545 plus x35 plus x45 equal to 450. This is based on the demand. So I need to deliver my item to node number 5, which is destination with node number 5, New York. It can either go from 3, which is the transshipment node number 3, or transshipment node number 4. Okay, it cannot go from anywhere else. Similar for the other destinations as well. And if you see x13 plus x23, so source 1 to transshipment point number 3, source 2 to transshipment point number 3 is equal to. So this is what is incoming into transshipment point number 3, and this is outgoing from 3 to 5, 3 to 6, and 3 to 7. So they should be equal. Incoming and outgoing should be equal, because you cannot store items in the transshipment point. And xij is greater than or equal to 0, because this is non-negativity rules. So this could be solved using any tool or any software to get an answer like. Next one is called transportation algorithm. Okay. Transportation algorithm is a procedure. It's an iterative procedure which is used to solve the transportation problem. Okay. And then you want to find out whether the solution is optimal or not. If the solution is not optimal, then you need to continue. You need to try to find something else. If not, you can stop. If it is an optimal solution, then we can stop the problem. So here is a representation here. This is a table you need to represent. Let us understand different elements of the table. This is the source from Des Moines and Evansville, and the 3 sources are given, and this is the destination. For each one, the cost is given. From this Des Moines or to Albuquerque is $5, and from Evansville to Boston is $4. So the cost is given. Cij is given in the small square boxes around. And then at the bottom, this is the demand like. Okay, this gives you the demand for each one. So demand for the first item, demand for the second one, demand for the third one. Here is the supply. Okay, what about the supply from each node can be how much? This is also given, and this cell represents the total. Okay, this cell 700 is the total of. So this one, if you add them, 300 plus 600 plus 100, 100 plus 300 plus 300, which is 700. 300 plus 200 plus 200 is also 700. Remember, the supply and the demand, if you sum them up, should be equal. If not, we need to do something else. Okay. If it is equal, if the supply and the demand is equal, it's called balanced problem. If it is not, it's called an unbalanced problem. So how to do it? The first step we got to do is find out what is called as an initial feasible solution. This could be done using a procedure called northwest corner rule. So let me explain the northwest corner rule. First thing is, you will take like from the top left, you will start from here. Allocate what you can allocate, the maximum you can allocate. So compare this 100 and 300. The minimum you can allocate is this 100. I mean, the maximum I can allocate is 100, which is based on the minimum between this 100 and 300. So you can see, exhaust the supply of each row before you go to the next one. So I have done this. Now the supply is finished. 100 has been allocated. Now come to this guy. Okay. So from here, I can allocate something here. How much? I can allocate 200. Remember, 100 plus 200 is equal to 300. I cannot cross this 300. So I can only allocate 200 here. And then there will be 100 left here, because I have allocated 200. 100 is left. I can allocate the 100 here. It is still less than this guy, so I can allocate. Then go to the next row. You have 300 here. This is finished already because this is 100, 200, which is finished. Here there's 100. So out of 200, 100 is allocated. So 100 could be allocated here. Remaining 200 comes here. So that will be the representation. Please note, we start from the supply. For each row, when you are finished, you go to the next row. So allocate it based on what you can allocate. So I will repeat it here. 100 is the supply, 300 is the demand, minimum is 100, so I can allocate it here for the first top left column, top left cell, and nothing more to allocate here. So because 100 is finished, this row is finished now. Go to the next row. This is 300, this is 300. There's only 100 allocated, so I can allocate here 200. I allocate here 200. Then now this is finished because 100 plus 200 is 300. This is accomplished now. But this is not accomplished because it is 300. I have only allocated 200. Remaining 100 I can allocate here because it is still less than this. I can allocate here. Then this is finished. 200 plus 100, which is 300. So this is also complete. Next row. Here I can allocate what? 100 because this is already 100 there. Out of 200, 100 is allocated. So I can put 100 here. Remaining 100 I can, remaining 200 I can put here. That's it. This is called initial representation, initial feasible table. Okay. Whether this is optimal or not is a different deal. So now we will start calculating the total cost. Just multiply 100 into 5 plus 200 into 8 plus 100 into 4 plus 100 into 7 plus 200 into 5. You get 4,200. It's a feasible solution, but it might be or might not be an optimal solution. So next step, how to find whether it is optimal or not, how to get the optimal solution. We have a method called stepping stone method. This is an iterative method. You start from the initial feasible solution to get the optimal feasible solution. First thing, we need to figure out whether there is any improvement possible. What do you mean by improvement? Is basically we can reduce the cost. If it's a maximization problem, if it's a minimization problem, you want to reduce the cost. Okay, let's see whether you can reduce the cost. Until we reach an optimal solution, we'll continue. So let's start step number 1. There is a very important rule which is called as the number of occupied cells available, occupied squares in the table, in the initial feasible table. You have to see is equal to number of rows plus number of columns minus 1. If it is not, if the number of occupied cells is less, then the solution is called degenerate solution. Okay, that's a name given. So here you can go up here, you can check 1, 2, 3, 4, 5. So there are 3 rows, 3 columns. Please don't add the supply and the demand. So 3 plus 3 is 6, 6 minus 1 is 5. So it's equal. So no problem. It's not a degenerate problem. So we will start to do what is called stepping stone method. To do the stepping stone method, we have used what is called as the unused squares. Not the used ones, unused square. Okay. So here is the step. Let me explain it with an example as well. So select an unused square. You have to start from that square. We need to make what is called closed path. And from the unused square, you put plus, then minus, and alternatively you should continue. Then we will calculate what is called improvement index. So let's do it in this example. So what is important is you have to find a closed path. Okay. So you can only use in the closed path, the starting point will be an unused cell. All the others you have should be an used cell. And there is only one closed path for each square we want to test. So let's start with an example here. So this is our initial feasible solution. Let's say I take this square. Okay. So I will point it as plus here. Then I can go here, then go here, then go here, then go here. So I'm making a square. I'm making a closed loop. That's all. It's not a square even. It can be non-square sometimes. So you are making what is called as a closed loop. I'm closing it. Remember, except at this starting point, all others are used cells, not unused. They are used cells. So for this point, I can make this. So starting, I will write here plus. Go here, I write minus, then plus, then minus. So finish. Loop is finished. So what does it mean? If I add a 1 here, for example, then because I'm going to get from this guy, this will become minus. So 99, 1 will go here. Because this become 99, this will become 201 to satisfy this criteria, 300 here. Then because this becomes 201, this becomes 99. And it's already 1 here, so that is satisfied. Okay. So you can see, you can do like this. From 100, I can send 1 here. Because I took 1 here, this should be removed also. Okay. Then this will get 201, get 1 increment. Here 1 reduction. So minus get reduction, plus gets increment. So now the point is, should I increment 1? Should I increment 10? I don't know. So how to do it, we will see in the next step. So what is the improvement you will get by doing this step? You can do like this. 1 into 4. This is plus 1 into $4. Minus 1 into, because we reduced 1 here. minus 1 into $5, plus 1 into $8, minus 1 into $4. So the solution will be plus 3. So our cost will increase by plus 3. So you can see here, so this is called as the improvement index. We started with 1 point dB, which is D is the source and B is the destination. So we have like plus $3. Is this good? We want to increase our cost or we want to decrease our cost? We want to actually decrease our cost. So let's do it for many of those unused cells. Okay. So let's take, we have this point here. We can go from here. Remember, I cannot go to this point from here because this is unused cell. In the closed loop, only the starting one will be an unused cell. All others will be an used cell. So I go here, which is plus, become minus, then plus, then minus, then plus, then minus, and close. You can try from here straight here. You go here, it's unused, so cannot do this. Go here to here, then go here, then here, like this. You can try all the options, but you will have only one closed loop per unused cell. So calculate this: plus 3, minus 5, plus 8, minus 4, plus 7, minus 5. You get $1 plus $4. Okay. So you'll try for all the other loops here. So now if you do that, you find that most of them is positive except one which is negative. Okay. Take the one that is negative. That is the point here. You will take which gives you negative. Let's say we have more than one that gives you negative, then in that case you choose the one that has the largest negative value. So largest improvement is what you take. Then from at that point, now we need to allocate. Previous time I showed you how to allocate 1. From 100 become 99, then you allocate 1. Now how much is the value I can allocate? The amount I can allocate is, look for the minus signs around, the cells which has minus. Among them, which cell has the smallest number, okay, that is chosen. So here you can see in this example, let's say we are using this root here, plus minus like this. So we started from here, basically went this way. So among them, look at the negative ones only, not the positive, only the negative. So this is minus, the value here is 100 allocated, not the cost, the value allocated. Here it is minus, the value is 200. So we will take this value here, okay. 100 is the value you choose now. So the value you choose, you allocate that number, okay. You add it to the point, to those which has minus, okay. So sorry, to those which has plus, you add it. So this minus 100, this is minus, which is 100. Take this is minus 200. So minimum among those minus points is 100. So you put here plus becomes 100. To this minus points you reduce it. This become 200 minus 100 becomes 100. This is a plus, so 100 plus 100 becomes 200. 100 minus 100, this becomes 0. So this becomes 0, 200, 100 and 100 here. So this will be the representation, okay. Anything that is 0 becomes an empty cell now. Now you calculate 100 into 5 plus 100 into 8, 100 into 9, 200 into 4, 200 into 5. Now the total value gets, shipment cost becomes 4,000, okay. So you can see initially we started with what is called initial feasible solution. For the initial feasible solution, we calculate the cost, possible cost. It was 4,200. Now we have reduced the cost from 4,000 to 4,200 to 4,000. So we have reduced it. So this is our aim, we want to reduce. Now we are going to see whether this is the optimal solution, whether we can go still further or not. Okay. So next step, this may be or might not be optimal. Then you start looking at other unused cells. Repeat the same stepping stone procedure. Again for this, try to form what is called as a closed loop. Again for the next point, okay. From here, you can go here, go down here, and then here, and so on. So form the closed loop and then calculate what is called as improvement index, then check with the improvement index. If you find something as a negative value, so that means the improvement index is negative, means there is still chance of improvement. Okay, take the ones that is negative. As I have told you, if you have repeated negatives, then you will take the one which has the maximum negative value. If you have two values which are negative, take the maximum negative. So it says E to C, so we take this E to C, this one here. Again, which is plus minus things. Look for the minus ones with the minimal one. This is 100 is the minimum most one. So what do you do? For plus you add 100, for minus you subtract 100. This will become 100, this will become 100 as well. 200 minus 100 will become 100, 0 plus 100 will become 100 here. This will be 100 minus 100 will become 0, 100 plus 100 will become 200. So now you calculate the cost and then you get 3,900. Still the cost has reduced. Again repeat, you want to find whether it is optimal solution. Again take for each points. You look for the stepping stone procedure, you find the closed loop, calculate the improvement index, you find all the improvement index is positive. So if it is positive or equal to 0, that means there is nothing to do, okay. So that means the solution we have got is optimal, you can stop there. If it gets equal to 0, then it means there is a possibility that there is an alternate optimal solution. There are 2 or more optimal solutions. Right, so this is a summary. In the case of transportation algorithm, you have to do what is called as, so if you want to do minimization, set up a balanced transportation table, use the northwest corner method to allocate initial solution, then do what is called a stepping stone, okay. So if you are doing minimization, if all the values are non-negative, you can stop. This is minimization. The previous one we saw is maximization. So if it is non-negative, then you can stop. And previous one we saw is also minimization. So if it is non-negative, you can stop. You have found the optimal solution. If any of them is negative, you can still continue. So this is just a summary. You can have what is called unbalanced transportation problem. Meaning here, you will have the total demand is not equal to the total supply. Okay. In this case, you need to add what is called dummy sources or dummy destination. If the supply is greater than the demand, then a dummy destination can be added. If suppose the demand is greater than the supply, then you can add a dummy source, okay. So you can add them. For these dummy sources or dummy destination, we will assign the cost factor Cij will be 0, okay, because it can never be submitted or it can never be used. So here is an example where they are trying to show that they want to show an example where you can check. If you see, add this 300 plus 200 plus 200, which is 700. But if you see the supply 300 plus 300 plus 250, it should be 850. But the total this side is not. So we add a dummy warehouse, okay, just to make the sum to be 0. All the cost factor will be 0 here. And that's what they have explained here. So this is somewhat analogous to adding a slack variable. If you remember, we have discussed slack in the previous chapters. And demand can also be greater than supply. If in that case, we add an extra entity as well. Like for example, here if you add the supply, it is 450, the demand is 500, so this is not enough. So we need to add an extra source, okay, with all of them as 0. Put the value, the balance, so you get supply should be equal to demand. Degeneracy in transportation problem, this is like the number of squares that is occupied is less than the number of rows plus number of columns minus 1. Okay, this could be possible during the initial solution or even during the subsequent solutions. So if you want to do this, you need to correct it with some special procedures, and it will be impossible if you have a situation like this. Then you cannot solve it using the stepping stone method unless you do the changes. So how to do it? To handle degenerate problem, create an artificially occupied cell. How to do it? Just put a 0. Take a cell which is unused now. Just put a 0 there. How do you choose such a cell? Okay. So you got to choose such a cell that it can make a closed loop for you. Okay. So that it will make closed loop. If not, then it's of no use. If you choose a shell and put it as 0, then it will have no use there. So here is an example you can see here. You have 1, 2, 3, 4 entries in the table. Number of customers is 3, number of warehouses is 3. So 3 plus 3 is 6, minus 1, you have 5. So you should have at least 5 cells which are filled. Only 4 of them is filled. So you can choose some, one cell, unused cell, and put a 0 there. So you can form some kind of, stepping stone can be applied. Otherwise, you will not be able to apply a stepping stone method here. So you can choose either here or here to allocate a cell there. So this is the example which is given here. And degeneracy is also possible during later cells also, okay. This is always a possible case, because if suppose you have 2 nodes which have negative representation using the closed loop, and both of them have the same value, let's say 100 and 100. So we will subtract, okay, the value, and both of them will lose the value, okay. If they have the same, then they will lose the value, so that both of them will become 0. It is possible sometimes. Here is an example given where the factory index is given as minus 15, so you can take the negative here, and we start. So if you start allocating, you can see here, minus here, this is from where you will start, plus, minus, you will see the minimum most minus. So this is 50, this is 50, minimum is 50 also. So you will add here 50, add here 50, this will become 80, this will become 50, but this will become 0, this will also become 0. So when these 2 points become 0, there will be 2 zeros, so the number of cells immediately drops. Okay, you lose 2 cells, so this will generate degeneracy. Sometimes it is possible that you have more than one solution for transportation, more than one optimal solution. This can be found out by looking at the improvement index. If the improvement index of a specific entity becomes 0, that means that it's optimal, more than one. If there are more than one optimal solution, it gives you flexibility, so you can choose between each one of them. Next is about maximization transportation problem. Here we want to maximize the profit, not like the previous case, which is minimization. You can go for maximization. Okay. Now you can decide that the optimal solution is reached when all the improvement index is negative or 0. And we always choose the largest positive index to use it to change the values using the stepping stone approach. There is also unacceptable or prohibited routes. Okay. And sometimes you will see you won't be able to send some data from one source to some specific destination. This is called unacceptable or prohibited route. You will find in the case of minimization problem, such prohibited route will have very high cost. Then you don't want to do it. In a maximization problem, again, it will be like very minimal, minus value, very high minus value. Then you cannot use it as well. Next, you have given what is called facility location analysis. So you can see, like, for example, I want to create a facility, I want to create something new, and I want to decide which one should be taken off, which one will give me the minimum cost so that I can recommend that one into my system. Like, here is a company which want to generate some few things, and the procedures, the new locations will yield lowest cost, and they want to create 3 plants or 2 plants, 2 new plants, and the places are Seattle and Birmingham. They already have some components at some places, they have warehouses available. So they want to choose whether to choose Seattle or whether to choose Birmingham. Okay. Among these, which one will give me a better price? And these are the data which is given. So production cost per unit in Seattle is 53, in Birmingham is 49, and the warehouse monthly demand is given. The production rate of the existing ones is given, and the total cost to produce in each one. Cincinnati takes $45, and each one is given as well. So you can see the monthly supply is this, the demand is high. So they need to produce some more. So they need to produce 46 minus 35, which is 11,000 units per month, either from Seattle or from Birmingham. They are not going to do both. They will only set up one unit, either from at Seattle or at Birmingham. So how to choose? They are also given you the dollars of expenditure. If I want to send from Cincinnati to Detroit, how much, and each one is given here. So let's solve this problem. So source destination, source is I, destination is J, Xij. From each of the source to each of the destinations is given here. And minimize the cost. So you can see, so to go from X11, which will be $73. What is X11? So one is, in this example, one is Cincinnati, and the destination is Detroit. So you can see the shipping cost is 25. Remember, you have to include not only the shipping cost, the production cost. At Cincinnati, the production is $45. So to produce one unit is $45. To transfer it to Detroit is $25. So you add these two together. Okay, 48 plus 25, you get 73. Similarly, X12, you have to see the production cost plus the transfer. Similar for each one of them. So this could be done. And Detroit, the demand of Detroit is 10,000, so you can say X11, X21. So the destination should be 1 because it is representing Detroit. And this is the demand, so it's always equal, not less than, not greater than. And Dallas, it is a number 2. So from anywhere to Dallas, and then from anywhere to New York, which is number 3, and Los Angeles is number 4. Cincinnati can supply 15K, so you'll say X11, 1, 2, 3, 4. So from 1 to 1, 1 to 2, 1 to 3, 1 to 4. Okay. So one is Cincinnati, one in the destination is Detroit. So accordingly, source is Cincinnati, destination is Detroit. And you can see this is less than or equal because it is the supply. Xij is greater than or equal to 0 because this means non-negativity. You can solve them, you can get an answer for it. So it is represented here. And most of the time you solve this using some kind of software or tools around. And you can see which one is the best to get best option there. So we can use some software. The next problem is called assignment algorithm. So here this is, we have discussed about what is called assignment method. Assignment problems have some kind of representation, who should be assigned to what. This could also be solved using some assignment algorithms like. Okay, an assignment problem is a transportation problem with the specific condition. in which the capacity from each source is 1 and the demand is also 1. So it's 1-to-1 mapping. We have seen this problem, fixed it shop before. There are 3 persons and they have different talents and they have to be allocated some jobs like 3 persons, 3 projects, okay? So you will find there's always the number of rows and number of columns will be equal in an assignment problem. So you will see number of rows is 3, number of columns is also 3. So how to solve this? So you can try different combination, which is called trial and error like. But the problem is it will go as a big number. It will be a combination problem. So if let's say there are 3, that is 3 factorial. If there is 10, then it will be 10 factorial. It will be very difficult to manage. So all the combinations can be tested and you can check which one is the minimal one. But this is not a very good approach. A better approach will be, an efficient approach will be what is called Hungarian method. It's also called as Fled's technique. Here what we do is this, it goes by the concept of matrix reduction. Initially we calculate what is called opportunity cost. From the opportunity cost, we will calculate which is the better choice to allocate. So how to calculate opportunity cost, we will discuss in the slides to come. Here, we want to find out what is the penalty by not assigning the best option to anybody. That's called opportunity cost. To calculate opportunity cost, so let's take a row. For a single row, find the minimal value. So here, take each row, row number 1, find the minimum one. Take the minimum cost and subtract it with every element of the row. So this is minimum is 6. So 11 minus 6 is 5, 14 minus 6 is 8, and 6 minus 6 is 0. Go to the next row, minimum is 8, so 8 minus 8, 10 minus 8, and 11 minus 8. And then in this row, the third row, minimum is 7, so subtract. So this becomes 2, this becomes 5, this becomes 0. So you got this answer, okay? So this is called the step 1 of the opportunity cost table, okay? The next step is you do it at the column level. Now you take for this column here, right, the minimum is 0, so there's nothing to subtract. For this column, let's say the minimum is 2, so start subtracting. This becomes 8 minus 2, which is 6, 2 minus 2 is 0, and then 5 minus 2, which is 3. And here, the third column, it is 0 is the minimum, so there is nothing to subtract. So this is what is called opportunity cost table. So step number 1 of Hungarian method is to generate what is called opportunity cost table. Find the smallest number in the row, subtract with all the elements. Do for each row, then you do for each column. Smallest number and subtract them. Now we will check whether we have got what is called as the optimal solution. How to find it, okay? So let's look at with an example. So here, based on the values given, you want to draw some vertical and horizontal lines, minimum number of vertical horizontal line, that will cover or that will hide all the zeros available. So if I want to draw minimum number of lines, okay? So here I have covered these 2 zeros with one line here. These 2 zeros with another line. So number of lines I'm using here is 2. If the number of lines is equal to number of rows or number of columns, that means I have achieved what is called optimal solution. Here it is not. The number of rows or number of columns is equal to 3 and number of lines is equal to 2. So I have not achieved what is called as optimal solution. If you have not achieved the optimal solution, there is a next step to follow. Look at those points which are not covered by the line, okay? So look for whichever is not covered by the line. So in this table here, so which is not covered, 5, 6, 2 and 3, the minimum one is 2. Take this value and subtract it with all the values here. So this will become 3, this will become 4, this will become 0, this will become 1. And add the number, the minimum number, to the intersection of the lines. If you have 2, 3 intersection, for all the intersection points. Only the intersection, not at individual line crossing points. So here this is the only intersection, so we will add this value, 2 to that value, okay. So that becomes 5 here. So now we try to do what is called as covering the lines, okay, covering the 0 with the lines. So you'll put 1 line here, 2 lines here, and here the last one, because this 0 will be empty. So you will have like 3 lines, or you can draw like this, 1, 2, 3, minimum ones, okay. So number of lines that is covering is 3, and number of rows and number of columns is 3. So that means we have achieved what is called as optimal solution. Now we need to know whom should be given what job. That is not clear. So how to make the final assignment, okay? The final assignment you can do like this. Go to a row which contains only 1 0, okay? So for the Adam, there's only 1 0. So 0 means you can allocate him. So Adam can be allocated to project 3. Once 3 has been allocated to Adam, 3 cannot be allocated to anybody else. Similar, Adam cannot be allocated to any other project, okay? So it's gone. Now looking at the others, Brown has project 1 and 2, both are zeros here. Cooper has project 1, project 3 has been allocated already, so that is gone. So this guy has only 1 0, so allocate Cooper to project 1. So one Cooper is allocated, Brown is left up with project 2. So allocate project 2 to Brown, and that's it. And find the cost of it. So sum them up. This is the optimal solution. Okay, you can also solve this using any other tool like. So again, here we can have what is called unbalanced assignment problem. Okay, similar like before. Number of rows, number of columns. If they are not equal, then you need to add dummy columns or dummy row based on what you want to add. Okay, if the number of tasks exceeds the number of people, add a dummy row. If the number of people exceeds the number of tasks, then you add a dummy column. Okay, here is an example where we want to add a dummy row because you have 4 people, but there are only 3 projects. And remember, assignment problem, the number of rows and number of columns should be same. Next, if you want to do maximization assignment problems, there are some other procedures as well. If you want to obtain what is called maximization assignment problem, you can do like before. You can obtain what is called as the opportunity cost. This is again subtracting from the largest single number. Then you can use it to assign the further things as well. So here is an example. Let's take this example. Here we have 4 ships and 4 sectors. We want to allocate them. This is what is called maximization problem. Again, we need to convert the maximization table into what is called minimizing opportunity cost. See, we want to follow the minimization approach with the maximization. So to do this, we got to convert the given table because this is maximization problem. To do this, convert it into what is called as minimizing opportunity cost table. So how to do it? Take the largest number from the table. Okay, the largest number here is 100. Right? Take the number and subtract everything from that number. So 100 minus 20 become 80, 100 minus 60 become 40, and so on. This will be 0. So you got this value. So this is done, taking the largest number and from that number subtract everything. All right? So every other number is subtracted from the largest number. Now we can do what is called as minimum number of, then we can follow what is called as the opportunity cost table as usual before. Take the smallest number in each row, then you start subtracting. So here you can see the smallest number is 40. So this will become 80 minus 40. Then this is 0, this is 10, this is 5 for each row. Then you do for each column as before, something like before. Then you try to put lines around and cover the lines. If you have number of lines is equal to number of rows or number of columns, then it is optimal solution. Otherwise, it is not. Next, we will discuss what is called as maximum flow problem. Okay. So if let's say I have a source, I have a destination, what is the maximum amount of something I can send? Like for example, how many cards can go or how much amount of data you can transfer from source to destination in a computer network. This could be solved using what is called linear programming like before, or you can also solve using maximum flow technique, maximal flow problem and a maximal flow technique. So to solve it, you are given a graph like this. In here you say your starting point is 1 and you want to go through 6. So if you want to go from 1 to 2, you can have the flow is 3, which means 300 cars can go. 2 to 6, it is 200 cars. But if you go from 6 to 2, it is 200 cars here because of this 2 here. And 2 to 1, it is 100 cars. Okay. If it says 0, that means I cannot take anything from 4 to 1. So let's start. You can start any source. Okay. Start any path from, pick any path from the source to the destination. Okay. So choose any path now. So let's say this is the path. You want to go from 1 to 6. So I say 1 to 6. So how to sort it out? Among this, 1 to 2, it is with 3. 2 to 6 is with 2. Okay. And 6 to 2 is with 2, which is 200 cars. 2 to 1 is 1. Now you find out which one is in the forward direction. Okay. Which one is the minimal value? The minimal value is 2. So take this minimal value, subtract it in the forward direction and add it in the reverse direction. So in the forward, this becomes 2 minus 2. This becomes 3 minus 2. Here 2 plus 2. Here 1 plus 2. So this will be like 1, 3, 0 and 4. Alright, do you understand? Here the point is in the forward direction from 1, 2 and 6. Take the minimal one. Subtract it in the forward direction and add that value in the reverse direction. So this is the point. You have one factor is the flow that can come from that node, it goes to the other direction. So for example, from 1 to 2, number 1 states you can have 100 cars. Okay, number 2 to 6, 0 means there can be nothing that can flow from 2 to 6. And from 6 to 2, you can do the reverse. Number 4 by 6 tells us the total by which we can reduce. is 2 here. So basically you can see, you can go 100, that is 0 here. If you go from this side, reverse direction, so it means you can actually reduce it by 2 because we got 2 from the previous representation. Here it is 2, so you can reduce it by 2. That's the meaning here. So I will repeat number 1 here, node 1 and 2. Number 1 here states there can be 100 cars here in this direction, flow from 1 to 2. And for 2 to 6, it is 0. So it means you can have 0 cars going. From 2 to 6, there can be nothing that can go. From 6 to 2, there is a number 4 by the node 6. That means that tells us the total by which we can reduce either the flow from 2 to 6 or increase the flow from 6 to 2. See, it can be both. Either you can do from this direction or this direction, okay? So we can reduce the flow from 2 to 6 or increase from 6 to 2. So if it says this side means I can increase this direction and I can decrease on the other side. So 4 here, I can increase this side, but I can decrease the other side. So this is what you have to do. Since we have indicated that there will be currently only 200 cars flowing from 2 to 6, the maximum we can reduce is only 2. This is what you have seen in this diagram. You are just explaining that step here. And from 2 to 1, you can see number 3 by node 2 tells us that is possibility of 3. And you want to reduce it, okay, from 1 to 2, or you can also increase it on the other side. So similar, now you will take another route, okay, from 1 to 6, 1, 2, 4, 6. Take the forward direction, minimal 1, subtract it in the forward direction and add it to the reverse direction, okay. So this could be done as well. So you can see, basically what happens now, it says 1 to 2 and 6, you have maximum capacity along the path is 1. So meaning you have like 3 units now, 3 cars can go. 1 car can go through 200 cars, can go through 1, 2 and 6, which is this route here, 1, 2 and 6. And 100 cars can go through 1, 2, 4 and 6, okay. So 100 plus 200, you have 300 now. Can we still increase? Yes, there's a route 1, 3, 5, 6. So you can try that route as well. So in this route, you can see it is 10, 0, 2, 1. So this is the minimal value. So this becomes 8 on the forward direction. This becomes 0. This becomes 2. This becomes 3. So that is 200 you will get from there. So you can add that 200 plus 100 plus 200, total capacity of number of cars that can go from 1 to 6 through different paths is 500. This is called maximum flow procedure. You can also solve the same thing using linear program. Just put them in terms of variables 1, 2, 3, 4, 5, 6. So from 1 to 2, 2 to 3 and so on and so forth. You have 1 to 2, you can also have 2 to 1. So both ways are possible. Accordingly, the rates are assigned. So 1 to 3 should be, 1 to 2 should be less than or equal to 3. And 1 to 3 should be less than or equal to 10. So from the initial values, you get all this. So 1 to 2 should be less than or equal to 3. Maximum is 3. And 1 to 3 should be less than or equal to 10. 1 to 4 should be less than or equal to 2 and so on. Remember, our achievement is to send the data from 6 to 1. So that is maximization of the flow. Okay, you want to send it from 6 to 1. So each one is represented, each arc is represented. And remember, if a packet comes to node 1, input and output should be the same. x21 to plus x61 minus x12 plus x13 plus x14 is equal to 0. So if you go across here, so you can represent here, right? 1 to 2, 1 to 4, 1 to 3. So what is coming is this direction. It can be like 6, 1. So you can see here x21 coming from 2 plus x61 minus x12 going from 1 to 2, 1 to 3, 1 to 4 is equal to 0. So you can represent all these flow in, flow out of each node. Like for example, if you take node number 1, okay, node number 1, remember this 6 is connected to 1. So it will be like coming in is from 6 to 1 plus 2 to 1. There is no 4 to 1, there is no 3 to 1 because it is 0 here. Okay, so it's not possible. And 1 to 2, 1 to 4, 1 to 3. So x12, x14, x13 should be equal to x61 and x21. Okay. So similar you can find for all the nodes, and you can represent it as a linear programming problem, and you can solve it. Xij is greater than or equal to 1. You can solve it using some tools also. Next is called shortest route problem. Here we want to find the shortest distance from one place to another. This can be modeled as a linear problem with 0 and 1 variables. It's a special type of what is called transshipment problem. You can also use some specialized algorithms. Here is an example. Somebody want to transfer some items from a plant to a warehouse, and the cost is also given for each one, and you want to find the shortest distance. How to solve it? Using the shortest route technique. Take the origin node, start from the first node, find whichever is the closest to you, okay, to that node. From 1, I can go to 3 with 200, and 2 is 200, so I choose this guy, which is a minimal one. Take the minimal distance, take it up. From now, you look for the other nodes which can be connected. I can go to 3, 5, or 4. The minimum one is here, 50, because 1 to 3 is 150, but 1 to 3 here is 200, so I will choose this guy. So it becomes 1, 2, and 3, this road, 150 is the distance. Then from there, look for the other nodes. I can still join 4, I can still join 5. But if you see from this route, it will be 150 plus 40, 190. Always start from the source. Or you can do like 100 plus 100 is 200. Or if I go like this, this is high, which is 100 plus 200 is 300. So you choose this route here, this one. So 135, which is 190. Next, you can try to reach 6. Okay, you want to reach the 6. You can also try 4, but still will be a higher value, right? So if you go from here, 150, 190, and then 100, 290. So this is the shortest path, shortest route technique. So this is one way of using it. If you have 2 points giving the same value, then you can choose any one at random. So this could be solved using linear programming as well. So represent xij. If it is 1 means it is selected. If it is 0 means it's not selected. Again, we have 1, 2, 3, 4, 5, 6 for each nodes. From 1 to 1, it's no point because 1 is the starting point. From 6, you don't go anywhere. So 6 is not in the from list. Source 1, 2, 3, 4, 5. Destination 2 to 6. 6 is the destination. From 6, you don't go anywhere. Similar, you don't, the 1 is not a destination. You don't reach 1. 1 is the starting point. Like. So here is the point. Original point from x12 to x13 is equal to 1. Okay. Origin, you can either go to from 1, you can go to 2 or to 3. Not to both, any one of them. Similar, from 4, you will reach 6, or 5, you will reach 6. So you can see from here, 4 to 6 or 5 to 6, 1 to 2 or 1 to 3. Okay, these two can be generated from there. Then for every intermediary node, entering and leaving is the same. So it will be x12 plus x32, for example, is equal to x24, x25, and x23. Okay, so each one you can represent it. Remember, this graph is bidirectional. You can go in both directions. You can bring the right hand side to the left hand side and equate it to 0. So here again, from x1 to 2, it is 100 miles, or the distance is given. So 100 into x12, 200 x13 for each one of them. And you represent all the other representations here. All the constraints are represented here. And all the variables can be either 0 or 1. You can solve it using some tools like. Next is called minimal spanning tree problem. Here you want to connect all the points of a network while minimizing the total distance. Here again, we can use linear programming, but it becomes a little bit complex. So if you will prefer to use what is called minimum spanning tree technique. So here, how to do minimum spanning tree. This is the algorithm is explained in this slide, but we will take an example to understand it. Take any node. This is given, the places are given and the cost is also given, or the distance is given to you here. Take arbitrarily select any node. Okay. Then you connect it to the nearest node from there, nearest node. From now, at that point, you connect to the next nearest node. Okay. Nearest to it. And then from there, you can connect the next nearest. So each one you can connect them. So you can see here in this scenario, you take 1, from 1, 3 is the closest. Then connecting nodes 1 and 3, connect 4, which is the nearest unconnected node. So you connect it. Okay, continue connecting all the unconnected nodes, right? So nearest unconnected node to 1, 3, and 4 is, that is 2 here, you can connect, or you can connect 6 as well. Again, if you have same numbers, you can choose any one. Remember here, we are not counting from the origin point, just from any point, okay? The point that is connected. From the connected, you choose any unconnected one, the closest one. Here then you can choose this guy, 5. You could also choose this guy, but you have started with this, then you have gone here. Then you can go continue. choosing the closest node. So you can represent it in a table like this. Start with 1, okay? Then the unconnected nodes are given. Then the closest one is number 3, which is not connected, so add it to the list. And then you can add it. Then you can see the length, and you calculate the total distance as well. So at the end, you will find the total distance to reach every node in the list. So on the unconnected nodes is reduced because we don't want to add the same node 2 times, okay, more than once. Again, you can solve it. So this is all about in this chapter. You can discuss, you have discussed LP. We also discuss how to sort things in different formats of this algorithm.